Well, now that we know something about parametric equations, we're going to talk about how we can use calculus on parametric equations, and specifically we're going to start with derivatives. So in our discussion here is really derivatives and slope of a tangent line. So suppose we have a parametric curve that I've drawn here on the left side, and suppose that we wanted to find the slope of the tangent line to the curve at this position. Okay? Well, let's assume that we're given our parametric equations. Let's assume that x is some function of t, and y is some function of t as well. Now, let me point out to you that this is what's going to happen, is we're going to make, the idea is that normally when we're dealing with derivatives, when we want to find, okay, I guess I need to say this first. We're looking to find the derivative of y with respect to x, but of course we don't have y defined in terms of x. So here is what we need to know first, and we'll get right to the details here in just a second. But we're assuming, although we don't have it written that way, we're assuming that y can be defined in terms of x. If we were to eliminate the parameter, we maybe have y is equal to something about x. Well, then based on that, and we know x is a function of t, so that means y is really a function of t that we already know. But according to the chain rule, okay, according to the chain rule, here is the idea of what's going on. According to the chain rule, there's a relationship, okay, a relationship between the derivative of y with respect to t, the derivative of y with respect to x, and the derivative of x with respect to t. Now remember, we're assuming y can be written as a function of x. But so under those circumstances, let's just say this, that the derivative of y with respect to t, and we're thinking of y as being a function of x, but x is a function of t. So we're using the chain rule there. We'd first have to find the derivative of y with respect to x, and then we'd have to multiply that, because x is defined in terms of t, with the derivative of x with respect to t. Now, this is a statement of the chain rule. And if we look at that, then what we could do is that we could solve for the derivative of y with respect to x. And that would tell, and the issue here, and by what? Dividing both sides by the derivative of x with respect to t. So here we have the derivative of y with respect to x is the derivative of y with respect to t, divided by the derivative of x with respect to t. And we know both x and y are defined in terms of t, so we ought to be able to find those derivatives, hence the derivative of y with respect to x. Now don't mistake this. This is not taking the derivative of a numerator and the derivative of a denominator. It's something completely different than that. Of course, this is only true provided that the denominator is not 0, that is, the derivative of x with respect to t is not equal to 0. But this is what we need to keep in mind when we're going about and doing this calculation for the derivative of y with respect to x. That's what we're going to be using. So we'll look at an example. Okay, for the parametric equation or curve, x equal t plus 2 cosine t along with y equal t cubed plus 4 sine t, we're to find the point x comma y, the derivative of y with respect to x, and the second derivative of y with respect to x, all at the t value of 0. Now, I've put in here find the point x comma y because when we're looking at the curve, we don't want to worry about finding, at a particular t value where we are on the curve and what tangent line it is we're finding. So we'll start out very simply, and this is not difficult at all. When t is equal to 0, we can find the x and y values. Remember, we're looking for that point x comma y, so we just need the x value and the y value. And of course, x is defined as t plus 2 times cosine t, so in this case it would be 0 plus 2 times cosine of 0, and of course that value is just going to be 2. And y is defined as t cubed plus 4 times sine t, so here we have, remember t is 0, so we have y as 0 cubed plus 4 times sine of 0, and of course sine of 0 is 0 also. So here we get a y value of 2. So the point that we're discussing this derivative at, the point is the point x with a value of 2 and y a value of 0. So we've finished the first part of this problem. Now, we need to find next. Okay, we want to find the derivative of y with respect to x. But since that's equal to the derivative of y with respect to t divided by the derivative of x with respect to t, then we need to find each of those derivatives separately. So our job changes now. To do this, we need the derivative of y with respect to t. And so we look at our y value up above, being t cubed plus 4 sine t. Well, the derivative of y with respect to t then would be a 3t squared plus a 4 times the derivative of sine of t, which is simply just cosine of t. And the derivative of x with respect to t, well, we just simply look above, x being t plus 2 cosine t. The derivative with respect to t will be a 1 plus 2 times the derivative of cosine t, but derivative of cosine is negative sine, so we end up with 1 minus 2 sine of t. Well, then that information gives us this. Okay. From there we have the derivative of y with respect to x being the derivative of y with respect to t divided by derivative of y with x, with respect to t. We get the fraction 3t squared plus 4 cosine t divided by 1 minus 2 times sine of t. Now, what we were asked to do here is find the derivative of y with respect to x at t equals 0. So the next thing we're doing then is we're taking that derivative and evaluating it at t equals 0. Well, of course, that's at the point 2 comma 0, because we know when t is equal to 0, that's the point we're talking about. But in this case, we have our derivative defined in terms of t, so we're evaluating it at t value of 0. So we simply do some calculations here. We would have 3 times 0 squared plus 4 times the cosine of 0 divided by 1 minus 2 times the sine of 0. And of course, in the numerator, we end up with just a 4, and in the denominator, we end up with just a 1. Actually, we end up with what, a 0 plus 4 times 1. Denominator is actually 1 minus 2 times 0. The bottom line is we have 4 over 1, or 4. Well, that can be interpreted as the slope of the tangent line at the point 2, 0. Now, before we do the last part, which is the second derivative of y with respect to x, I'd like to put up a little sketch of what this curve looks like, and I need a little more space to do that. By the way, I've done this in Maple. I'll sketch it, and then maybe I can get a graph to come up from Maple software, MapleSoft. But let me tell you the way we would do parametric equations in Maple. We use the plot command. Okay, so plot. Remember, we've got would have to be in the command mode here. But we've got would use plot, and then open our parentheses. And here we would now we're going to put in the parametric equation. So we open a bracket, and we put the x definition in, the x value, x of t, and then we put the y definition in terms of t, and actually it doesn't have to be in terms of t, it could be some other parameter name, and then we put the limitations on the parameter itself. For instance, like t could be from 0 to, remember it's dot pi, and now we're finished with the definition of our parametric curve equations. So we close the bracket. And next we put in the values of our horizontal variable x in this case. We might say, okay, we're going to let the x's go from -10 to +10. And then next we put in the parameters, the scaling for our vertical component, and here I could maybe say -10 to 10, and then we could put in some options. Options. For instance, we could say something, and the next would be our options, but it might be something like color is equal to red, and then we close the parentheses. So let me remind you that this is for the parameter, and if we weren't putting any limitations on the parameter, we could actually say anywhere from -infinity dot, not 3 dots, just 2, right? My bad, just 2 dots. Remember, this is for the horizontal variable, okay? This is the horizontal variable limitations, and this is the vertical variable, limitations, and here's where we would have options. Okay, what other options we might have? In this particular case, I'm using the command plot, open parentheses. Our x was defined as t plus 2 cosine t. And our y value is defined as t cubed, or is defined, plus 4 times sine of t. And for our parameter, t, we didn't put any limitations on it, so I'm going to say t is equal to -infinity dot infinity. Okay, so now I close the brackets. I've completed the definition for my parametric equations. Now I've got to put in my values for x that I'm going to graph under, and I'm going to say x is going to go from -5 to +5. And my y values, -30 to +40. And then close my parentheses. And when I do, then I'll get a graph something like this. Well, I've got a real rough sketch of this, and I'll try to make it look a little better here. I can give you a real computer-generated version in a moment. But also, by the way, of course, this command will not give us the direction, but I'm going to let you know the direction or orientation of this curve is in this fashion. Okay, that's what it looks like. Now, here's what we've done. This isn't really very good, but here's what we've done. At the point 2, 0, see, what we found out is when t is equal to 0, we're at the point 2, 0, which is this place where, of course, we're crossing the x-axis. And we just found out the slope right there is 4. That's what we just found out. So that is, if we had a tangent line right there, the slope of that tangent line would be 4. Okay, that's what we ended up doing. Now, next we want to find the second derivative when t is equal to 0. And that's got its own little issues with it, but second derivative says something about concavity, doesn't it? So if we get a second derivative that's positive, we would be concave up. If we get a second derivative that's negative, would be concave down. If we get a second derivative that's 0, that would be an inflection point, so we could be moving from concave up to concave down. But here it looks like we're actually going to be concave up, so we're expecting a second derivative to be positive. But finding a second derivative is another matter altogether. So let me kind of point out more generally what we did. And remember, x and y are going to be defined in terms of parametric equations. So let's kind of see what we did. Assuming that x and y are defined in terms of a parameter, we found the derivative of y with respect to x. Okay, that's what we were doing, derivative of y with respect to x. And the parameter is t. So what I would like you to do is think about the way we did this. What we're taking the derivative of y, we found that derivative with respect to t. And then the variable we were finding the derivative with respect to, we found the derivative of that variable also with respect to the parameter. So it could be written this way. If we are dealing with the derivative of some function, we'll just say a right now, okay? We're dealing with the derivative of some function that's defined in terms of t with respect to the variable x that's also defined in terms of t, or the parameter, then we'd simply take the derivative of that function with respect to t and divide it by the derivative of x with respect to t, or the parameter. Parameter doesn't always have to be t. Now, the issue here then is, suppose we were taking the derivative of the derivative. See, let's just assume that's what we're doing. Isn't that a second derivative? Well, what we just went through is, okay, first we take the derivative of the function with respect to the parameter. Whatever we're taking the derivative of, we take the derivative of it with respect to the parameter. Now, the derivative of x with respect to y, we've already found, is a function with respect to t. It's defined in terms of t. So we take the derivative of that function, okay, with respect to the parameter t, and we would divide that by the derivative of, now what are we taking with respect to x? So we take the derivative of x with respect to the same parameter t. And that's a big deal, okay? So let's write this on the next page as we get ready to finish this problem. I know I just said this, but I can't say it enough. So I'm going to repeat what I did and what I said, and in this fashion. When we're asked to find the second derivative of y with respect to x, okay, now x, we've got parametric equations in terms of x and y. For finding the second derivative of y with respect to x, well, that's doing nothing more than asking us to find the derivative of the first derivative. the derivative with respect to x. So we're finding the derivative of the derivative of y with respect to x, and we're finding that with respect to x. Well, derivative of y with respect to x is a function. Say, derivative of y with respect to x is a function of t. Let's not get all wrapped up into it happens to already be the derivative. And x is a function of t. And that's what we're taking the derivative with respect to. And so the way this works is we take the derivative of what we're taking the derivative of. That is, we're taking the derivative of the derivative with respect to t. But here it's the derivative of y with respect to x. We take the derivative of it, and we divide by, well, now we're taking the derivative with respect to x, that variable being x. We take the derivative of that variable with respect to the same parameter. So, as I said, I can't say that enough. This is a critical issue for you to remember, okay? Anytime you're looking for a second derivative, when we're talking about parametric equations. Okay, well, back to our problem. In our problem, we're finding the second derivative of y with respect to x. And as just stated then, that's the derivative of, okay? So here's what we've got. This is kind of a mess. We've got the derivative with respect to t of the first derivative. And the first derivative was the fraction, the quotient 3t squared plus 4 cosine t divided by 1 minus 2 sine t. I kind of crunched that up accidentally. And below, of course, we have the derivative of x with respect to t. And the derivative of x with respect to t, we already know the value of, because we created that derivative a while ago, didn't we? And so that result was 1 minus 2 sine t. Now, to find the derivative of the derivative with respect to t, we have to use the quotient rule. And so it's going to be its own mess. It's going to be long and messy. So we're taking the derivative of quotient, so we take its denominator, 1 minus 2 sine t, and we multiply it with the derivative of the numerator, okay? And in that case, we get, check me out, we'll get 6t to the first power minus 4 times the sine of t. And then we subtract from that. We'll take the numerator, and don't change it, so we take 3t squared plus 4 cosine of t, it's getting very crunched, I recognize, times the derivative of the denominator. And the derivative of the denominator ends up being negative 2 cosine t. And I really feel bad that I've got that crunched up. And we divide all of that by the denominator squared. Oh my goodness. Let me see if I can write that a little more neatly over here. Put my equal sign here. Now notice that if we multiply by the reciprocal of our denominator of the big fraction, we're actually going to end up with what? 1 minus 2 sine of t to the third power in our denominator. And our numerator is going to be nothing more. Let me write it so we can read it. 1 minus 2 times the quantity 2 times sine t times 6t minus 4 times the sine of t minus the quantity 3t squared plus 4 times the cosine of t. Oh, but we have times a negative sign, so we could actually change this to a plus right here, couldn't we? So we'll say times positive 2 cosine t. Now we could kind of be concerned a little bit and think, how in the world are we ever going to simplify this? But all we were really asked to do is to find the derivative, the second derivative of y with respect to x, evaluated at a t value of 0. So we don't really need to worry about simplifying. We just need to do some substitutions. So in this case, we'll have 1 minus 2 times the sine of 0, which is 0. And we'll have 6 times t, which is 0, minus 4 times the sine of 0, which is 0, plus 3 times t squared, 0 squared, plus 4 times the cosine of 0, which is 1. And then multiply that with 2 times the cosine of 0, which is 1. And all that's divided by 1 minus 2 times the sine of 0, which is 0, and all of that's cubed. So as I simplify this, we have a 1 in this position. This first position is a 1, isn't it? So we have a 1. All of this is a 0. So times a 0 plus what we have here is a 4. So times a 4 times a 2. And all that's divided by a 1 cubed. And so we simply get the value 8. Well, that's something by itself, but specifically then, we know the curve, as we anticipated, the curve is concave up at the point 2, 0. After all, that's when t is equal to 0, isn't it? When t is equal to 0, we're at the point 2, 0. And we know the curve is concave up because the second derivative is positive. Well, this problem, we're supposed to find the equation. It doesn't say that, I guess. The equation of the tangent line or lines to the parametric curve given by x equal t to the 5th minus 4t cubed and y equal t squared at the point 0, 4. Now remember when we find it, so what do we need? We need certainly a slope of the tangent line or lines, and we need a point. And we don't have any problem with the point. What we have a problem with, of course, is the slope. And to find the slope, we've got to find the derivative of x with respect to y, which requires us finding the derivative the derivative of y with respect to x, which also requires us to know the derivative of y with respect to t and the derivative of x with respect to t. So, and the derivative of y with respect to x is going to be in terms of t. So what that tells us is that we have to know what t value gives us, or values give us the graph, give us the point 0, 4. For what value of t is the graph at the point 0, 4. That's the first thing we have to be concerned about. Well, at 0, 4, that means x is 0. And if x is 0, that means that 0 is equal to t to the 5th minus 4t cubed. Well, if we solve that equation for t, that tells us t is 0 or positive 2 or negative 2. I mean, of course, yes. Look, there's a common factor of t, isn't there? So if I factor out the common factor of t cubed, actually, I'd have t cubed times t squared minus 4 equals 0. And of course, the t values that make that true would be 0 and either positive or negative 2. So it appears there's actually 3 different t values when we have an x value of 0. An x value of 0. Let's be a little bit careful, though. When y is 0, y is 4. So that implies that we have 4 is equal to t squared, because y is t squared. Well, that implies the results there would t can be either plus or minus 2. So the issue is that when t is either positive or negative 2, we are at, or the graph is at, the point 0, 4. When t is 0, we have a different y value. We have a y value 0. So that doesn't follow then, does it? So there's actually 2 different times that we have, that 2 different t values were at that point. Now, normally we're not going to have the graph in front of us, but it will be easy for us to, I'm going to sketch the graph here so that we can see what that gives us. So here you can see what the graph actually looks like, and of course the point 0, 4 is this point right here. And now it makes sense. By the way, the orientation of this graph is moving along this direction. It goes through that point, it continues along this direction, then it comes back up and goes along this direction and goes through that point again. So we're at this point when t is equal to negative 2 the first time, and then at t equals 0, we're down here at t equals 0, and then we come back through this point as we're going back up at t equal positive 2. So I put the t equals 0 there because that was a place where we found out we had an x value of 0, but of course the y value is 0 as well. So we found out there's 2 different t values that we go through that point. So there are clearly 2 different tangent lines, aren't there? The first time we go through that point, we have a tangent line to the curve that looks something like this. And the second time we go through that point, we have a tangent line to the curve that looks something like this. So we're actually going to have 2 different tangent lines. One's going to have a positive slope and one's going to have a negative slope. So what we have to do next, of course, is to find the derivative. And then we'll calculate the slope after we find the derivative. Well, remember the way we calculate derivative. The derivative of y with respect to x is the derivative of y with respect to t divided by the derivative of x with respect to t. So when we're calculating the derivative of y with respect to x, we look above and find out, well, since y is t squared, the derivative of y with respect to t is simply 2t. And since the derivative of x with respect to t, we look above, x is t to the 5th minus 4t cubed. Well, the derivative of x then is 5t to the 4th minus 12t squared. So that's the derivative. Pardon me. That's the derivative of y with respect to x. Well, so one of the slopes we need to calculate, one of the slopes we're going to calculate the derivative of y with respect to x evaluated at the t value of -2. And when we do that, we'll have 2 times -2 in the numerator, and in the denominator, we'll have 5 times -2 to the 4th power, which is a 16, minus 12 times 2 -2 to the 2nd power, which is, of course, 4. And that ought to give us, let's double check, that's a -4 divided by 5 times 16 is 80, minus 48, and I believe that's a -4 over a 32, which is -1/8. So that's the slope of one of the 2 tangent lines. And in the other case, the derivative of y with respect to x, we need to evaluate that at a t value of +2. Well, here we'll have 2 times a +2 for our t, and in the denominator we'll have 5 times t to the 4th, and t to the 4th, in this case 2 to the 4th is 16 again, minus 12 times t squared, but since t is 2, we'll have a t squared of 4 again, and in this case we'll get a +1/8. So one of these tangent lines has a -1/8 slope, and the other has a +1/8 slope. So in the case of the -1/8 slope, then of course in our point, remember our point is 0, 4, isn't it? So we would get y minus 4 is equal to our slope, -1/8 times x minus 0. And when we simplify that and rearrange it, we'll have y is equal to -1/8 x plus 4. Well, here is the tangent line that has the negative slope. So the equation of this tangent line is y equal -1/8 x plus 4. Now in the other case, when our slope, the slope of our tangent line is +1/8, and of course we still are using the point 0, 4, then we have y minus 4 is equal to +1/8 times x minus 0. And of course when we simplify this time, we'll have y is equal to a +1/8 x plus a 4. And so that's the equation of the other tangent line, y equal +1/8 x plus 4. Equation of each of those tangent lines. And so that's the reason at the very beginning I said find the tangent lines, which may have been unclear. Clearly we can have a graph go through one point multiple times when we're talking about parametric equations. So we could have multiple tangent lines, multiple slopes. Well, as we continue this discussion, we need to talk about horizontal and vertical tangent lines. We'll actually look at another graph here in a moment to determine that. So let's pause and start that on the next page.